So thanks everyone for making it to this workshop. I hope everyone is having a great day too here in R Medicine. My name is Joy Payton, and I am on the organizing committee of this conference. And on behalf of everyone behind the scenes, we want to say thank you for your participation. Thank you for attending. And I know many of you, like me, work with large data sets like electronic health records. And a lot of times these large data sets are behind the scenes stored using relational database systems. And SQL, the principal way we interrogate these systems, has been around since the 1970s. And SQL shows no signs of going away anytime soon. And that's why I'm really glad that Chris Battiston is so generously offering his experience and his wisdom today in this workshop on first steps in SQL with R. So Chris, we're really excited to learn from you today. And with that, I will pass the mic to you. So thank you so
Thank you.
much for giving us your wisdom today.
Thank you so much, Joy, and thanks to everybody for being here today. Let me pull up my screen here. And I wouldn't necessarily, I have wisdom, more, okay, don't do this or do this because this is what I've learned has worked. Um, and okay, do you see my screen?
We do, yep.
Excellent. All right, let's get started here. So, as Joy mentioned, my talk is called First Steps with SQL in R, Making Data Talk. My email address is chris.battiston@wchospital.ca, and I am currently the REDCap administrator and research data analyst at the Research Institute at Women's College Hospital in Toronto, Canada. Been here for approximately 10 years, but I've been a DBA and using SQL for 25 years. So it's something that I've learned by accident, and that's one of the reasons why I really like SQL. So let's get started into this. So who am I? I realized I was supposed to do an actual running of the code during this session, but having ongoing issues with my R environment since I upgraded to 4.5.0, I know, lesson learned, don't upgrade before a demo, but here we are. So anyway, I've incorporated all these slides with my code and have made the code available to you. You can grab the slides and the files for the workshop at my GitHub page, which I will post in the chat. So GitHub page is in the chat there. It's also in the footer of the slides if you've downloaded the slides and forget where everything is. That GitHub repository is not going anywhere. It's also my first GitHub, so please be kind on formatting and the way I've structured things. Just a quick intro on myself. My background is in clinical data systems, especially, as I mentioned, platforms like REDCap. I spend a lot of time working at the intersection of research, compliance, and technology. Our REDCap environment is Health Canada regulated, and as a result, I do have to do a lot of work to make sure that we are compliant. One thing I really try and champion is communication first data workflows. That means not just making sure that data is clean and valid, which of course is essential, but also making sure it's understandable and actionable for the people who actually use it. My goal is to make data more expressive, something that tells a story, not just something that passes a validation checkmark. And when I'm not up to my eyeballs in REDCap or R, you'll probably find me chasing my almost 6-year-old around the park or listening to way too much heavy metal, drinking way too much coffee. So we'll start with, here's a quick overview of how we'll move through the workshop today. We'll start with section 0, learning the language. This is where we'll get grounded in the terminology and the structure of our data, making sure we know what we're working with. Then in section 1, listening to the data, we'll look at how to let the data speak, focusing on summaries, distributions, and the kinds of questions the data is naturally ready to answer. Section 2 will cover understanding relationships, where we'll dig into how variables connect. looking at joins, links across tables, and what those relationships can mean. Section 3 is all about spotting patterns. This is where we move beyond rows and columns and start seeing trends, clusters, or gaps, whether that's over time, across categories, or between groups. And section 4, we will be talking about building the story. So how do we translate the analysis into actionable insight? This is about communication, charts, visuals, and talking points that make your data easy to understand and act upon. Section 5, we will compare and reflect, where we'll step back and look at what we've done, comparing outcomes, methods, and thinking critically about what we've learned. Then we'll move into the wrap up and next steps, where we'll highlight practical ways you can apply this back in your own projects. Finally, I'll leave you with a set of resources and practice tools you can use to keep building on what we have covered today. I will be keeping an eye on the chat as well. So if you do have questions, please feel free to post in the chat. I've got 3 monitors, so I'll do my best to keep an eye on that as well. Okay, so I want to start with a guiding principle that I come back to over and over again. Good data tells the truth. Great data tells a story. Good data is clean, complete, and technically sound. It passes validation. It lines up in the database. It gives us the facts, and that's essential. But facts on their own aren't always enough because good data might tell you what happened, but great data tells you why it matters. Great data has structure, yes, but it also has a voice. It has clarity. It leads someone, a clinician, a researcher, a decision maker, from confusion to understanding and ideally to action. And that's really the goal of today's session. Not just to clean the data or to validate the form or to merge the tables, but to listen to what the data is telling us, to find the patterns, the relationships, the signals, and then shape that into something meaningful. So as we go through each section, I want you to keep that in mind. We're not just working with variables, we're working with potential stories. Your job, our job, is to help those stories come through. So before we dive in, let's talk about why SQL matters in this context. SQL stands for Structured Query Language. It's the standard language used to work with structured tabular data, the kind of data we see in REDCap, exports, clinical databases, and most spreadsheets or flat files. What makes SQL so powerful is that it's designed for asking questions, especially relational questions. Things like, how do these two tables connect? What happened before and after this event? Which records meet this specific condition? In that sense, SQL complements R really well. R is fantastic for analysis, modeling, and visualization. SQL is great for organizing and extracting the data you want to work with before you do all of that. And here's the best part. SQL is portable. Whether you're working with REDCap data, a hospital system, an EHR, a data warehouse, or even Excel files loaded into R, SQL is used across all of them. So if you learn it here, you can apply it almost anywhere. Bottom line, SQL helps you get the right data in the right shape for the job. And once you have that, everything else flows a lot more smoothly. I always think it's helpful to know where tools like SQL come from, especially something that's been around this long and is still going strong. SQL was originally developed at IBM in the 1970s by Donald Chamberlain and Raymond Boyce. They were building on the work of E.F. Codd, who introduced the idea of the relational model, a way of thinking about data in terms of tables, rows, and relationships between them. That model became the foundation for most modern databases, and SQL was the language designed to interact with those systems. By 1986, SQL had become so widely adopted that it was formalized as an ANSI standard, and it's still one of the most widely used data languages today across industries, platforms, and systems. What's impressive is that while the syntax has evolved a bit over the decades, the core principles behind SQL haven't changed much. The idea of selecting, filtering, grouping, and joining data is just as relevant now as it was in the early days, whether you're working in a healthcare setting, doing research, or building software. I think it's really helpful to set expectations up front, to be clear about what SQL is and what it isn't, because sometimes people come to SQL expecting it to behave like a programming language or like R and then get frustrated when it doesn't. So let's break it down. On our left, SQL is declarative. That means you don't tell it how to do things. You just describe what you want. Give me all the rows where age is over 65, or sum these values grouped by county. You're describing the result, and the database engine figures out the steps. It's also optimized for tabular data, anything that fits neatly into rows and columns. Think spreadsheets, REDCap exports, databases. It's incredibly good at that. It's also very readable and easy to share. SQL code is closer to plain English than most other tools, which makes it a great choice when you're collaborating or documenting your workflow. And finally, SQL is great with joins, which is one of its superpowers. If you're working with data across multiple tables or forms, SQL is probably the cleanest way to link it all together. Now, on the right, here is what SQL isn't. It's not a full programming language. You can't build an app or a simulation or a full data pipeline in SQL alone. You'll usually pair it with something else like R or Python to get the full picture. It's not ideal for unstructured data like free text, images, or PDFs. You can store that kind of data in a database, but querying it gets really tricky and very messy. It's not built for graphics or statistical models. That's where R really shines. SQL will give you the right slice of data, but R is what you use to visualize it and dig deeper. And finally, it's less flexible than R. It's powerful within its domain, but it's not meant to do everything. So think of SQL as your starting point. It helps you extract and shape your data so you can analyze, visualize, and tell the story more effectively with tools like R. Now that we know what SQL is and isn't, let's break down some of the core building blocks you'll use every day. Think of these as the fundamental commands that let you ask your data exactly what you want. Select. This is how you choose which columns or variables you want to see in your output. For example, you might want just the patient ID and total charges, not every single column. From. This tells SQL which table to look in. If you think of your data as a spreadsheet, this is where you say which sheet to pull from. Where. This is how you filter rows. Basically, select only the records that meet a specific condition or conditions. For example, only patients older than 65 or only records from a certain county. Order by. This lets you sort your results. Maybe you want to see the highest charges first or sort patients alphabetically by last name. Group by. This is a key command for aggregation or summarization. It lets you group rows based on one or more columns so you can get sums, averages, or counts for each group. Joins. This is how you merge data from multiple tables, like connecting patient info from one table with lab results in another. Joins are essential for combining relational data. These core commands form the backbone of almost every SQL query you'll write. As we go on, we'll see them in action with real data examples. Okay, let's take a quick look at how SQL can use yeah of how to use SQL right inside R with the sqldf package. There are a number of other SQL packages that you can use within R. I've used sqldf now for at least 5 years and have never needed to go to one of the other packages. But each package comes with pros and cons. One of the downsides to using the sqldf package is that the last update was in 2022, but I've never had a problem with it, and I've never run into an issue where it couldn't do what I wanted it to. So first thing you need to do is install the package if you haven't already, and you can do that with the install packages.sqldf command, which I will post in the chat here. And then you're going to call it as you normally do, just using the library sqldf command. Here I'm loading a CSV file called hospitaldata._nyc.csv. This is a sample data set from a very, very large big data compilation called the Sparks database from New York State. And this is where I've subsetted some of the data from that particular package. Using sqldf, I write a query directly as a string inside R. So in this case, my query is select distinct facility name, age group from hospital, limit 5, where this selects distinct combinations of facility name and age group from the hospital data and limits the output to just 5 rows so it's easy to look at. Using sqldf is really handy because it lets you leverage familiar SQL syntax to quickly filter, summarize, and explore your data all within your R workflow. No separate database needed. The package that I'm using here actually creates a temporary SQL database in your backend of R. You do not necessarily need to know about that. You don't have to interact with it directly. All you're doing is querying your data frames or your data as you normally would and using this in R. Okay, so now that we've covered some basics, let's apply these SQL skills to explore real-world data from New York City hospitals. In this section, we'll focus on 3 key SQL commands. Select to pick the columns we want, where to filter the rows based on conditions, and order by to sort our results. Our goal is to answer some practical questions like which are the 5 top hospitals by procedure type? What are the most common procedures performed? How do our charges vary by patient age and race? These questions are typical of the kinds of insights clinical data managers, analysts, and researchers need to extract regularly. By the end of this section, you'll see how combining these SQL commands can quickly surface valuable insights from complex data sets. So let's walk through this query step by step. What I'm showing here is select facility name, count star as freak from hospital, group by facility name, order by freak descending, limit of 5. So first, select facility name and count star as freak tells us that SQL to return each hospital's name along with the count of how many records or procedures they have in the data. This count is then labeled as freak, which is short for frequency. Next, from hospital specifies the data set that we're querying. Then, group by facility name groups all the rows by hospital name so the counts are calculated per hospital. Order by freak descending sorts the results by frequency from highest to lowest so the busiest hospitals come first. What you're seeing here is Mount Sinai Hospital has a frequency of 50,110, followed by New York Presbyterian Columbia at 44,167, and so on. Now let's shift our focus to the procedures themselves. This query that I've shown here selects CCSR procedure description count start as freak from hospital, group by CCSR procedure description, order by freak descending, limit by 5 again, uses the select to pull the procedure descriptions along the count of how often each procedure appears, labeling again that count as freak. As before, from hospital, group by, and order by freak dense do the same thing. We're just using different variables. In this case, the NA is showing as the top value at 185,742, spontaneous vaginal delivery at 55,614, vaccinations, then administrative of therapeutic substances, and in the last of the top 5 is cesarean sections. Next, let's explore how charges vary across different demographics groups, specifically by age and race. I should highlight here, being Canadian, I don't necessarily know or have to worry about costs and charges because our healthcare system is very different, but I do think it is an interesting variable to use as part of this analysis. So here's a query that groups the data by race and age group, counting the number of records in each group. So I'm saying select race, age group, count star as freak from hospital group by race and age, order by freak again, descending limited by 5. Again, this is not anything too complicated, and it's basically the same thing. We're just building on and adding in new variables. Finally, the output is limited, and while this query counts the frequency, we can potentially modify it to sum up total charges for these groups to better understand where the highest charges occur. This kind of breakdown is key for uncovering disparities or patterns in healthcare utilization and costs, and we'll go through all of that later in this workshop. So again, if I'm counting the frequency of costs, white 70 or older has a total count of 106,394. Other race 50 to 69, other race 30 to 49, and so on. One of the foundational strengths of SQL is the ability to combine data from multiple tables through what we call joins. In real-world data sets, information is often spread across different tables. For example, fact demographic or patient demographics might be in one table, procedures in another, and billing details in yet another. Joins let us bring these pieces together to get a complete picture. Let's walk through the main types of joins you'll possibly encounter. Inner join. This join returns only the rows where there is a matching key in both tables. Imagine that you have a table of patients and a table of hospital visits. An inner join on patient ID will give you only those patients who actually have visit records. If a patient has no visits, they won't appear in the results. This is useful when you want to focus only on entities with related data in both tables. Left join. This one returns all the rows from the left table plus any matching rows from the right table. If there's no match, you still get the left table's row, but with missing null values for the right table columns. For example, if you want a list of all patients regardless of whether they had visits, you'd do a left join from the patient table to the visits. This helps in identifying patients without any visits. Right join. This is basically the mirror image of a left join. It returns all the rows from the right table plus matching rows on the left. It's less commonly used but handy in some scenarios. However, a quick heads up, sqldf, where the R package we're using for SQL, does not support right joins. So if you're saying B right join A, you'd have to write it as A left join B. Full outer join. This join returns all the rows from both tables, matching where possible, and filling in missing data with nulls where there is no match. It's like combining a left and a right join, ensuring nothing is left out. This is especially useful when you want a comprehensive view of all records from both tables, even if they don't align perfectly. So you may have A, B, C in one table and then have B, D, E in the other table, but it'll show the joined data where it's appropriately joined. Cross join. This join returns every possible combination of rows between the two tables, or a Cartesian product. It's rarely used directly because it can produce huge data sets quickly, but it's useful for generating combinations or for testing. Important note, again, when using the sqldf package in R, you'll only have access to the inner join and left joins. More advanced joins like right join or full outer join require a full SQL engine such as PostgreSQL, MySQL, or a complete SQLite installation outside of sqldf. Mastering joins is essential because your data will almost never be in a single flat table. Being able to relate tables effectively unlocks much richer and more insightful analyses. Now that we've learned about joins in theory, let's put it into practice with our hospital dataset. We'll start by loading an additional CSV file called hospital_nyc_counties.csv. This file contains information about counties, essentially geographic areas linked to the hospitals. You can import it using the standard read.csv syntax. And once we have both datasets loaded, hospitals and counties, we can combine them using a join. Here, the goal is to link each hospital record to its corresponding county name. The SQL query we're using is select h.facility name, c.hospital county from hospital H. And I should stress here that the H is just an alias to indicate that we're referring to the hospital table. You could write hospital.facility underscore name. That gets too busy, that gets too complicated. So one of the nice things about SQL is these aliases where you can refer to a table just as a single letter. And then inner join counties C on h.hospital county equals c.county ID. And again, the hospital county in the hospital table is 1, 2, 3, or 4. In the county table, we have 1, 2, 3, and 4 is equal to Manhattan, Bronx, Kings, etc. And we're going to limit it to 10 records. Breaking it down, we see the hospital's name, facility name from the hospital table, alias H. We also see the hospital county field from the counties table, alias C. The inner join connects these tables where the hospital's county ID matches the county's ID. Limit 10 again restricts the output to just 10 rows so we can quickly verify the join results. This join is crucial because it enriches our hospital data with geographic context, enabling us to perform analyses based on location. Practicing joins like this lays the foundation for integrating multiple data sources to build more comprehensive datasets for deeper insights. Let's now analyze which counties are associated with the highest total charges, a useful way to understand healthcare resource utilization across regions. Here's the SQL query we're using. Select c.hospital county, sum h.total charges as total charges from hospital H, inner join county C, again joining the two county IDs, group by hospital county, order by total charges descending. What we're doing here is we're selecting the county name again from the counties table. We're using the sum function on total charges from the hospital table, which is again aliased as H, to calculate the total charges aggregated by county. Again, the inner join ensures that we only include hospital records matched to valid counties. Group by, again, groups the data by the county, so the sum is calculated on a per county basis. And then finally, the order by total charges descending again sorts the total charges from highest to lowest, making it easy to identify the counties with the largest healthcare expenditures. This kind of analysis helps administrators and policymakers understand where the greatest healthcare costs are concentrated, which can guide resource allocation and planning. And it's no surprise that Manhattan has almost 4 times more than the other areas. And again, we'll dig into more of the Manhattan specific data shortly. Okay, we're going to take a quick 5-minute break here just to give everybody a chance to get more drinks and pause on where everybody is. We're going to dig into more of the data in a moment, but I will be here for any questions during the break or anything else that people want to talk about for the next 5 minutes. Okay, so it's now 11:31. If you could be back by 11:36 Eastern time, that'd be fantastic. Oh, Elizabeth, your question about where the A and the C in the front of the variable names comes from, that's just an arbitrary alias that you can use to designate how you want to refer to that particular table during the development and the execution of the query. So I typically recommend something that's a little descriptive. So in this case, I'm using C for county and H for hospitals. You could do HOSP for the hospital table. You could do count for the county tables. It's totally up to you. But it does make the code significantly easier to read and follow because you're able to track the variables. So rather than having to type hospital dot whatever, you can just do H and then refer to it within that query using that alias. Did that answer your question? Excellent. All right. It's now 11:36 Eastern time, so we're going to get back into this. Now we're going to get into the fun stuff. Now we're getting into the real hardcore. Let's geek out on SQL. So in this section, section 3, spotting patterns, we shift our focus from individual records to patterns and summaries within the data set. Rather than looking at single transactions or procedures, we now explore trends and aggregates that help us understand broader insights in healthcare utilization. As we've talked about, SQL provides powerful tools for summarization, including group by, which allows us to categorize and group records. But we also have aggregate functions such as average, count, and conditional counting using what's called count case. These techniques help us distill large amounts of data into key takeaways that are relevant for analysis and decision making. Specifically, in this section, we'll explore average cost per county to identify geographic variations in healthcare expenses, conditions by demographics to uncover disparities in healthcare access and treatment patterns across different racial and ethnic groups, and counts by category to see which diagnoses, procedures, or patient characteristics appear most frequently, helping to highlight high-impact areas of care. By the end of this section, you'll have a better grasp of how structured queries can summarize complex data sets, providing valuable insights that inform healthcare policies, hospital planning, and patient care strategies. In this section, we focus on how to summarize data and spot meaningful patterns by grouping records and calculating averages or counts. As we mentioned, we'll be using the average, count, and count case, which I'm displaying here an example of the average function. Select CCSR diagnosis description, average length of stay as AVG underscore days from obviously hospital. We're going to group by the CSSR description again and order it by average days descending, again, limit of 5. Breaking this down, we select the diagnosis description and calculate the average number of days patients stayed in the hospital for each diagnosis. The group by clause, again, groups the data, by the diagnosis, so the average length of stay is computed for each of the groups that we have specified. We then order the results by the average length of stay in descending order to highlight again diagnoses associated with the longest hospital stays. Finally, we limit the output again to the top 5 diagnoses for easier interpretation. And obviously you can set this limit to whatever you want, or you don't have to include the limit statement and just run it on everything and then see the entire data set or the results of the data set. So this approach helps identify which conditions tend to require longer hospitalizations, information that can be critical for both hospital management, patient care, planning, and resource allocation. In addition to the average length of stay, similar methods can be used to explore average costs per county or condition prevalence by demographic groups, helping us spot important patterns across the data. When we've run the data here, we've seen that other specified encounters in counseling, average length of day is 66 days. The other top 5 are all subsequent encounters for open wounds of trunk, poisoning by drugs, etc., with the range being from 23 to 30.7 days. One important consideration in this analysis is the filtering criteria applied to the data. To ensure accuracy and relevance, procedures lacking a description are excluded from the dataset. Additionally, cases where ethnicity is recorded as unknown are removed to maintain the integrity of the demographic comparisons. The dataset is organized through a grouping and aggregation process where records are categorized based on race, ethnicity, and procedure description. This structure allows for a more detailed examination of trends within the different populations, helping to highlight variations in medical procedure frequency and associated costs. A threshold for inclusion has been set to ensure statistical significance in the results. Only procedures with a count greater than 10,000 occurrences are considered in the final output. This measure presents small sample sizes from skewing the findings and helps maintain the reliability of the analysis. Finally, the ordering of results follows a structured approach where data is sorted by race, ethnicity, and procedure type. Organizing the information in this way facilitates comparisons across different demographic groups, allowing for clearer interpretations of potential disparities. One of the key takeaways from this analysis is that the data provides an opportunity to compare medical costs across racial and ethnic groups. These comparisons may uncover disparities in healthcare access, treatment patterns, or differences in pricing across procedures. By identifying such trends, decision makers can explore possible explanations for cost variations and address inequalities where necessary. Again, as an example, and I apologize that this is wrapped in this way, it's just long labels. So this first row is for Black and African American. Ethnicity is not Spanish Hispanic. It is administration of therapeutic uses, NEC. There's a total of 10,782 instances, with the average charges being $60,658, or the average cost being $18,745. So again, depending on how you've set your query up, depending on the criteria and the information that you need to extract, you can have various summary tables very easily and very quickly pulled. So this query analyzes patient severity of illness distribution across different age groups at Bellevue Hospital Center. This goal is to assess how illness severity varies within the facility and identify potential trends related to patient demographics. Through the filtering criteria, um, in this analysis ensure that, sorry, losing my screen here. The filtering criteria in this analysis ensure that only records from Bellevue Hospital Center are included. By narrowing the dataset to a single facility, the results provide a focused view of illness severity within that specified hospital, allowing for more precise comparison across age groups. Through grouping and aggregation, the data set is structured by facility name and age group. Oh, is my audio gone wonky? Can other people?
Maybe just for me, I don't know. It just got a
Okay,
little bit pixelated for me.
I do have that problem with Zoom, so I apologize if that's happening to folks right now. Um, okay, let me.
You're still readable. It's just a little staticky.
Okay, let me turn off my camera. Maybe that'll help. Is that any better?
Talk a little bit more and let's see.
Okay, let's keep going. If it gets worse, then I'll try something else.
Okie doke. We can hear you.
Okay,
So sally forth.
all right. Through grouping and aggregation, the dataset is structured by facility name and age group. Within each category, patient cases are classified based on severity of illness. The severity categories include minor, moderate, major, and extreme. Additionally, when there are cases where severity information is missing or marked as minor, are counted separately to maintain transparency in data reporting. A counting mechanism is applied to determine the number of patient cases within each severity category. This approach enables us to quantify the distribution of illness severity across age groups, highlighting potential patterns in patient health conditions. By capturing variations among age demographics, the results may reveal insights into the type of cases hospitals frequently encounter. The final ordering of results follows a structured format, sorting result records by facility name and age group. This sorting ensures clarity in data presentation and facilitates easy comparisons between different age groups, allowing healthcare professionals and analysts to examine shifts in illness severity across populations. One of the primary insights from this analysis is that the distribution of severity levels across age groups may indicate broader healthcare trends. For example, older patient groups might show a higher prevalence of major and extreme illness severities, potentially reflecting increased medical complexity among aging patients. Disparities in severity classifications may signal differences in hospital patient management strategies. Some hospitals might have treatment protocols that influence how patients are categorized within severity levels. Understanding these patterns can guide healthcare professionals in refining patient care approaches. Additionally, identifying trends in severity distribution at Bellevue Hospital Center can support hospital planning and resource allocation. If certain age groups consistently experience higher illness severity, hospital administrators may need to adjust staffing, bed availability, or specialized treatment options accordingly. And again, you can customize this output in any way that you want. So you can filter on where facility name equals New York Presbyterian or whatever the case is. One thing that I don't go through in this workshop, but might be relevant to folks is if you want to be able to use a search for anything that has New York Presbyterian, and I know there's 3 or 4 different hospitals that have that in their name, you could specify where facility underscore name like New York Presbyterian and then put a percent sign at the end of New York Presbyterian, and that will search for anything where the facility name starts with New York Presbyterian. If you do percent New York percent, then it will be anything that has New York, any part of the string. So again, it's one of those things where the criteria can be very, very complicated, but using SQL syntax, it's just where X equals Y, where A equals B, and so on and so forth, allowing for a great deal of flexibility and easier readability.
Chris, can I
Yeah,
interrupt just for a moment?
of course.
At the end of section 3, some folks have some questions about the availability of that code. Um, it looks as
Yes.
though maybe that specific code or that specific slide didn't make it into sort of the public link.
Uh, sorry about that, folks. Okay, let me post it in here. Is that the code that folks are referring to specifically?
I think so. I also confirmed, I just looked and I think maybe you just have like you need to, update, make sure that the GitHub is up to date with whatever
Or
your.
Cordo newbie, GitHub newbie, all sorts of newbie things for me. So yes, I will make sure that that gets updated, and apologize for that oversight on my part. So if you don't, I will try and do that today or tomorrow. But if you don't see them updated by end of day tomorrow, please do email me. I've just posted my email in the chat as well, and folks can just contact me and I'll send them the file.
Awesome. Thank you so much.
Yeah, no, sorry about that. Okay, so I had a 5 minute break, but we just had a 5 minute break, so I'm just going to keep going for a little bit. This section is on building the story, from query to visualization. So what we're looking at right now is code that performs an analysis of total hospital charges across different counties, grouped by race, and visualizes the results as using a bar chart. I should highlight here, I'm using Plotly. I do not normally use Plotly. I normally use ggplot2, but ggplot2 seems to have broken with my most recent upgrade to 4.5.0 of R and R Studio, so I just had to find an option, not alternative option, and Plotly seems to have done the trick and actually does a couple of things a little better than ggplot2, so lesson learned for me. The first part of this code that I'm showing here uses the sqldf function to execute a SQL query that retrieves total charges for each county and race combination from the hospital dataset. To ensure accurate county identification, again, I'm joining the query to the hospital dataset with the county's dataset using the county identifier. The data is grouped by hospital, county, and race, allowing for structured comparisons across different demographics. Additionally, a threshold is applied so that only records with more than 10,000 occurrences are included, again, ensuring our statistical significance in the results. The query orders the final output by hospital, county, and race to maintain clarity in the presentation. The second part of the code utilizes the Plotly package to create a bar chart that visually represents the summarized data. Within this visualization, the x-axis corresponds to hospital counties, while the y-axis displays total charges incurred by patients. Different races are assigned distinct colors to provide clear visual differentiation. To enhance user interaction, hover information is incorporated into the chart, allowing viewers to see specific values when hovering over the bars. Additionally, the layout settings establish a fixed width and height to control the display size, ensuring the chart remains readable and well structured. So now that we've extracted some summaries, meaningful summaries with the SQL, it's time to build the story visually. Data visualization turns raw numbers obviously into insights that are easier to understand and communicate. And here we are looking at the interactive bar chart. So as you hover over, it will tell you the total costs for that particular race and or for that particular hospital. Okay. Um, this query groups, sorry, hang on just a second here. I just lost my spot. So this approach helps us spot disparities or trends in charges across demographics groups and geographic regions, as I mentioned, which is a powerful way to tell the story hidden in the data. Interactive plots like this also let users drill down and explore the data dynamically, making the story even more accessible and making the story even stronger. To highlight some of the key insights and key observations, charges vary significantly by race across counties. The Bronx and Queens see the highest charges for other race, while Manhattan and Richmond see the highest charges for white race. Black and African American charges tend to be lower across most county except for Kings. And what does this imply, or what are the possible interpretations of this? These patterns may reflect disparities in healthcare access, cost structures, or utilization across racial groups. The data can inform healthcare equity efforts and policy decisions aimed at addressing systematic differences. And a conclusion that you might draw is the visualization highlights racial disparities in healthcare costs across hospital counties, providing insights for further study and intervention. I should highlight here that there's a couple of additional variables that we don't touch during this workshop, but things like Medicare and Medicaid are tracked. I believe there's 4 different levels of insurance that get documented. So you can look at the folks that have Medicare and Medicaid, how much they're paying, et cetera, et cetera. So one of the reasons why I absolutely love this data set and use it for multiple training sessions is that it really gives you real world applicability of what you're finding, but it also allows you to explore different cross sections of the data. And because it's maintained and hosted by New York State, it's obviously very reliable and well up to date. I think the last data pull was from 2023. So things like COVID data is available. There's other things that they've added in over time. So you can definitely have a full overview of the New York State healthcare system spanning, I think it's 10 or 15 years, looking at the same variables time over time. So again, depending on your questions, depending on your needs, pulling this into R and then using SQL can make your life a lot easier for analytics and data querying. Okay. In this example, we extend our data storytelling by incorporating multiple demographics factors into a single visualization. So first, we're going to use a SQL query to summarize the data again. I'm not going to go through this again, but basically it's looking at the same basic information as we've looked at previously. Um, we will then put this into a Plotly interactive chart where again, hospital counties on the x-axis, the y-axis will show average total charges. Bars are colored by race, allowing comparison between racial groups within each county. And the hover text will again show corresponding age group, providing additional context without cluttering the main view. This visualization will show us and allow us to explore patterns in healthcare charges across multiple dimensions, geography, race, and age all in one place. While this chart shows the group info on hover, further enhancements like faceting by age group or stacking bars could even provide even clearer insight. So let's look at the bar chart here. So some of the key observations include Manhattan has the highest average hospital charges across all racial groups. So Manhattan's here in the middle, and there are the three bar charts for the corresponding racial groups, and obviously they are well above any of the other groups. Richmond has the lowest average charges for other race and Black African American. Across most counties, white patients tend to have higher average charges compared to other groups. So what are the implications? The variation in hospital charges by county and race may reflect differences in healthcare costs, services provided, or insurance coverage. Understanding these disparities can help in assessing healthcare equity and identifying possible systemic barriers to access. Um, sorry, lost my spot again. Conclusions include things like this visualization highlights racial disparities in average hospital charges, providing a foundation for further discussion and policy development around healthcare fairness. So to take these two graphs that we've just looked at, both generated through Plotly and through sqldf, we can determine or we can come to a possible conclusion or to tell a story that Black African American patients tend to have both lower total and average hospital charges across most counties. This could reflect limited access to care, fewer hospital visits, or disparities in the intensity of treatment received. Other race patients show high total charges in areas like the Bronx and Queens, likely due to higher hospital usage. However, their average charges per visit are relatively low, suggesting frequent visits for lower cost care. White patients typically have higher average charges per visit, possibly indicating access to more expensive treatments or better insurance coverage. In counties like Manhattan and Richmond, they also show high total charges, suggesting both frequent use and higher cost care. A potential takeaway of this is that these patterns suggest that race is closely linked to healthcare cost and access. Disparities may stem from systemic factors such as insurance, income, or provider behavior, highlighting the need for more equitable healthcare policies and practices. And again, these are just assumptions. These are just based on a very small subset of the data that I'm looking at in order to actually come to these conclusions accurately and with transparency and integrity. You'd need to look at the bigger picture. You'd need to do a more deeper dive. So please don't take these as anything more than me trying to develop a story using this data and these queries through sqldf. Okay, so the next story that I'm going to be telling is using SQL-driven data processing, again with another interactive Plotly, to highlight total charges for hospital procedures across different counties again. But the goal this time is to show it in a different manner. Again, adding another page to your story, adding another layer to what you can provide if you were asked to do this sort of data pull. So in this query, step one is going to obviously extract the data using SQL. We're going to do the same thing as we've done previously, where the data set contains details on hospital procedures, the counties, obviously the counties. We're going to create, using Plotly, an actual interactive heat map, where once the query returns the structured data set, we can use Plotly to transform the data into a heat map to show these comparisons. So what are some of the key insights? And I'll show you the plot in a second. This visualization reveals which procedures drive the highest costs in specific regions. Darker colored regions indicate higher total charges, which might signify procedures, more complex treatments, or broader patient demand. Differences in cost patterns across counties could reflect economic factors, insurance coverage variations, or hospital specialization. And this approach elegantly combines SQL's data processing efficiency with Plotly's visual storytelling capabilities, offering a rich analytical tool for exploring healthcare expenses across geographies. So here's the visualization. As I mentioned, it is a interactive. So again, you can move over any of the bars to see specific information. This visualization provides a clear comparative view of medical expenditures, showing which procedures generate the highest cost across counties. It allows for the identification of healthcare disparities, as we've already talked about, pinpointing areas where expenses are significantly higher. The differences may be influenced by hospital specialization, as we've already talked about, but it allows people to understand where they may need to allocate resources more efficiently or develop strategies to address cost inequalities across different regions. So, section 5 is compare and reflect. So, in this case, I'm comparing SQL versus dplyr, which is one of R's most popular packages for data manipulation. Both are incredibly useful tools, and rather than thinking of them as competing, it's helpful to see them as complementary. SQL excels at handling relational data, especially joins across tables, summarizing large datasets inside databases, being portable across platforms. So from SQLite to PostgreSQL to SQL Server to MariaDB. dplyr, on the other hand, uses the pipe syntax, which makes logic easier to follow, especially when you're transforming data step by step. It is more intuitive for many R users, especially when exploring or wrangling data in memory. And the example here mirrors a basic SQL group by and order by, where I'm taking the hospital and I'm countering diagnosis and then grouping it descending. This gives us the most common diagnosis in the data set, obviously, but the same logic is used in the SQL select diagnosis. So it just shows the differences to get the same basic result. Ultimately, your choice depends on what you're doing. If you're inside R and working with one data set, dplyr may feel more natural. If you're pulling from multiple tables or need to query a database directly, SQL is still your best friend. So let's take a moment to summarize what we've covered to this point. First, we've learned how SQL helps us frame the right questions. It gives us the structure to think clearly about the relationships in our data, which is critical for clinical and operational decision making. We saw how sqldf makes it easy to bring SQL into R, letting us tap into SQL's strengths without leaving the R environment. We also explored how joins can create context. By linking tables like hospital data with county information, we enrich our dataset and uncover deeper stories. As for the next steps, if you're working with REDCap or other EDCs, try connecting queries to those data sets. Even if you're exporting CSVs, many of the same principles apply. And if you're ready for more power and more flexibility, consider diving into full relational databases, as I mentioned, like PostgreSQL or MySQL. These systems support more advanced SQL features and can handle larger, more complex data sets. Ultimately, the goal is to use SQL not just to clean data, but to understand it and tell better, more meaningful stories. Today, we explored SQL not just as a technical tool, but as a gateway to meaning. You saw how sqldf joins us, let us frame questions, connect data across tables, and surface patterns that might have otherwise stayed buried. We've practiced looking at things like structured clinical data and turning them into insights, and that process is where real impact begins. But beyond syntax and summaries, there's something more important at stake. Why storytelling matters in clinical research. As I mentioned earlier, good data tells the truth, great data tells a story. In clinical research, the truth often lies in rows and columns, coded values, cost fields, discharge records, but the story lives in why these numbers matter, who they represent, why they reveal, what they reveal, and how we can act on them. Every record represents a person, a patient, someone who came into a hospital, had a procedure, faced uncertainty, and left behind a trace in a data set. When we analyze this data, whether to study utilization, cost, equity, or outcomes, we're entrusted with a powerful responsibility. And storytelling is how we give back. When we tell the story well, we honor the people behind the data. When we see disparities, we have a chance to advocate. When we translate findings into action, we close the loop from data to insight to impact. As I mentioned earlier, there's a number of different resources that you can use to keep this momentum going, including a cheat sheet where I talk about SQL building blocks and examples, practice queries in a PDF, so 15 hands-on exercises to hone your skills that I've pulled from the slide deck. I've provided you the subset of the Sparks data set that I've used for the purposes of this, as well as the counties table. And I've provided the package sqldf documentation. So final thought for the slide deck is this is why we do what we do. Clinical data analysis isn't just numbers, it's narrative. And your job as a data practitioner or researcher is to surface meaning, communicate with purpose, and always remember who the data comes from. Let your work tell a story. Let that story serve. Okay, so I'm going to stop sharing for just a quick second. So it is now 12:08 Eastern Time. We're going to take a quick 5-minute, 7-minute break. So if you can come back at 12:15 or 15 after the hour, I'm actually going to pull up the um, data set, and we're going to work through a couple of manual examples, and I will answer any questions, show you anything that you'd like to see within the data set itself. So go grab another drink or sandwich or whatever the case is, and if you can be back at 15 after the hour, we will go into and do some manual work. Sandra, to answer your question, how would the exercise I just walked us through have changed if I'd used dplyr exclusively? To be perfectly honest, I've never had the need to use dplyr exclusively for work that I do. Um, as I mentioned earlier, I'm a DBA by accident, and I've been a database administrator for over 20 years, spending a lot of time on learning SQL. And that's one of the reasons why I started using R was because of the sqldf package. So when I need to manipulate or extract or clean my data, my go-to is always to use sqldf. There have been a couple of cases where I've needed to use dplyr because I needed to do that step-by-step data cleaning and data manipulation. But in my experience, using the data that I use, sqldf is the best option because it is, as I mentioned earlier, sort of that plain English programming language. It's easy to read. I can provide it in my documentation, and people know, even if they don't know SQL, they know exactly what I'm doing just by reading the query. So again, it's very much a what meets the needs that you need to deal with sort of scenario. So if you're comfortable using dplyr and it does what it needs to, then I would love for you to start using SQL because I think it's going to make life easier for you. But this is just a way to show you how you can do things maybe more efficiently, maybe more effectively, rather than relying on the tools that you've always gone to. I hope that answers your question. Okay, so what I'm doing in this case, oh, sure. Okay. Do you see my screen?
Yep, we can see your screen.
And it's our studio, it's nothing else.
No, you're all
So
good. You're all good.
excellent. All right. So what I'm doing here is, again, I'm grouping by hospital county. I'm selecting the age group. I am then taking the count when the type of admission is expired. Type of admission. No, patient disposition. Type of admission. Patient disposition. Again, you can do something every day for your entire life and you still make silly mistakes sometimes. So again, things like seeing a whole pile of zeros is a red flag to me that I made a mistake, and sure enough, I did. So let me rerun this. There we go. That's better. Okay, so we're looking at hospital county grouping by age group. I wanted to count by patients that had expired versus not expired. So if I look at the hospital data set and I look at the patient disposition, there's a number of different categories within this column, but I wanted to filter out those that were expired versus everything else. What I'm then looking at is I'm taking the average. And one of the nice things is that you can not only use count case, but you can use average case. So in this case, I'm saying average the records where type of admission is expired. Then if we're doing a count, you use then else null end, because you're going to say, if this record meets the criteria, count it as one. For averages, that doesn't make sense, because then if you're saying average then one, then you're just going to get all ones. What you need to do here is specify the variable that you want averaged. So what I'm saying here is average case when type of admission is expired, then average the length of stay as average stay expired. Do the same thing for those patients that are not expired. And then we want to see the total charges for the two groups as well. Obviously pulling from hospital, and then obviously doing the grouping and order by the two variables that we've specified. When I go into the results, hospital county, and again, because I have not mapped to the county's table, we're not seeing the labels, we're just seeing the coded values. We're just seeing the coded values from the table. Age group 0 to 17, 18 to 29, so on and so forth. The number that have expired, 54, 48, 557, 1683. And then for those that did not expire, count accordingly. For some reason, I am seeing NAs now for average length of stay, average stay expired. Why am I now seeing? Again, reasons why I hate live demos, because I see things like this, but the other one works and I just copied and pasted the code. Let me try. Hang on a second here, folks. Um, okay, why would that be happening? Oh, because I do actually have NAs. Ah, that's why. Okay. So again, telling your story. There's further investigation that would need to have happen because obviously you're going to have patients that have not have expired but have a length of stay. So you need to figure out why this is happening. And I'm not going to waste anybody's time trying to figure it out. Let me just try one other thing here. Let me just try. I don't know why this would work though. Let me just try running this. Nope, that didn't work either. So all of that to say, as good as you can be in a programming language, sometimes it throws you a curveball like this, and you need to dig in. And again, I'm not going to spend any time digging into this, but um, if this was a real case, I would definitely try and figure out why my average stay expired and my average charges expired are not updating. But all of that
Chris,
to, yeah,
is there an equivalent to like an NARM?
it's one of those things where I think so. But again, if the count is working, then I would have expected the same syntax to have worked for
Mm.
um, this. But let me try something here. Ba, 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 ba.
Oh, Milena has a question in chat.
Oh,
Is
yes.
type of admission, can type of admission be expired? Or
Oh,
is really that's a patient disposition that you're trying to
I'm going
measure?
to go back to bed now. Thank you very much. Yeah.
This is, but this is where teamwork comes together.
Absolutely. And I'm a team of one, so I'm often arguing with myself because I don't have anybody else that I can bounce ideas off of or talk to or anything like that. So let me clear the log, clear that. Try running this again. And if that doesn't work, I've got one other thing that I want to try, which there we go. Hey, look at that. Thank you, Milena. You've saved my sanity. Um, so again, good use case of know your data, keep your variables simple and self-descriptive. And if you get something that doesn't make sense, go back to the basics. So I was going to try and figure out how to do a coalesce because I thought maybe it was a problem with the NAs, but no, I was just pointing to the wrong variable. So thank you, Milena. So what we're looking at here now is, as I mentioned earlier, for Hospital County 1, for the age group 0 to 17, 54 expired, 21,960 not expired. Average stay for those that expired was 18.25 days. For not expired was 3.9 days. So a significant difference in the number of days. And looking at the amount of charges, 845,000 versus 60,000. So obviously there are very clear differences, and this would be very nicely put into a graph or onto a PowerPoint slide if you were looking at, summary tables. But all of that to say, if you provided, again, as I mentioned earlier, if you provided this to somebody that doesn't know SQL, they'd be very easily able to quickly see what you've done and how it was put together. Quick pause, see if there's any other questions. Anybody? Okay. Um,
I have a question.
yeah.
Um, one of the things that you've showed us is sometimes in some of your slides, you've had words like count and average in lowercase, and sometimes you've had it in uppercase. Um, can you speak to case sensitivity in SQL?
So I tried to make sure that if I was referring to the count function, that I was capitalizing it in the slides for emphasis, and that I was only using lowercase if I was referring to doing a count or doing an average. There is actually no case sensitivity in sqldf. It's one of the few packages that does not have case sensitivity. So you can use something like this. So if I did something like this, I would expect this to run. So there is no, it's not like other packages or other aspects of R where you have to be very careful about camel case or not camel case, lowercase, whatever. I use this simply for a way to emphasize those terms that are SQL specific. So if I'm looking at this, I know that anything that's lowercase is likely going to be a variable or a category. Anything that's capitalized is going to be SQL syntax. You can have it all on a single line. You can have it broken down the way I've got it here. This is just my preference for the formatting, but it does not require it in this particular format. I just like the layout of this because then I can, if I'm looking to troubleshoot, my eyes know where to go to find that having statement because I know where that is in the list of the sequence.
Thank you.
No problem. Anybody else have any other questions? All right, I will continue digging in. So this is the subset of the data that I've pulled together again. Again, I'm not going to show you, the same things over and over again, but basically you can have, if I had a, what's the data set survival? Hang on a second here, folks. Let me do something here. Library survival. Let me call up library survival. And sqldf select star from long. So if you're not familiar with the survival package, it is used for survival analyses. And there's a data set in that package called lung that you can use for various things. So in this case, what I'm going to show is something where you can do sqldf select, select star from lung where, and again, case sensitivity doesn't matter. I'm just writing this as an ad hoc query. Age is greater than or equal to 70 and time is less than 1,000 and time is greater than 200 or age is greater than or equal to 60 and time is greater than 1,000. So again, ad hoc query, just totally throwing this out there, but basically what this is saying is I want to see all the records where the patient age is greater or equal to 70 and time is between 200 and 1,000, or the age is greater than or equal to 60 and time is greater than 1,000. So you can have complex nested statements of ands or ors within your SQL query. And when I run this, I do get results. So I do have this person is over 70. Time is between the parameters that we've asked for. If I find, okay, let me change that to greater than 80, greater than or equal to 70, and time less than 1,000. Let's try that. Okay, so greater than 70, time is greater than 1,000. I've got two records that the patient's age is over 80 and their time is within the 200 to 1,000 day range. So you can have very, very complex criteria where you might be only returning count star a single result. So in this case, I've got 3. This is really nice for if you're doing exploratory data or if you just want to get a sense of what the data looks like. You can pull together various summary tables using SQL, excuse me, and then explore those particular categories a little more in detail. If you wanted to, you could then have something like age as count. Group by age, order by age. And again, case sensitivity here doesn't matter. So I'm just doing this as a quick ad hoc age count. What I can then do, for example, is expand that even further. So if I take out the age criteria, and let's take out the age criteria for this one, and you can then do something like average age, ba, 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 ba. pH, Arno, group by pH kernel, pH kernel. Oops. No such column as pH kernel. What the heck's going on? All right, so this is just showing you that although we have pH kernel in the data set, occasionally you do need to, and I believe it's backticks, so let me try backticks. And this is where if you're running into issues, you've got to know the data. And this is where I always stress with my users and with my trainees that I teach and everybody else, the more comfortable you are with the data, the more you'll be able to quickly resolve and identify issues in this case. So in this case, average age is 63, pH kernel is 50. But what if we wanted to take an average of the pH kernel? Can I do that using AVG? And if I take this out, because we don't need this, because we're just pulling the average. Yep, so there it is there. So again, depending on your requirements, depending on what you need to extract from the data set, there's a pile of different things that you can do very, very quickly. I don't know what this would look like if you were doing this using dplyr or one of the other packages. Again, I use what I know, and what I know is SQL, so this is what I rely on for things like this. The other thing that you might want to do is if you want to do data cleaning. So select star SQL select select star from lung. Okay, so going back to the lung full data set here, I'm going to put this into a lung2 data frame. Okay, so we've now got this as a lung2 data frame. What I'm going to do is lung sqldf update lung2 set we're going to set age equals to 70 where age is less than 80. So what I'm doing here is if you need to clean your data, one of the nice things in SQL is this ability to run update queries. Oh, that's new. Huh. That used to work in SQL. All right, well, that's something else that I'm gonna have to look into. However, all is not lost because what you can do is select star case when age greater than or equal to 70 and age is less than 80. Put then 70 and as age 2 from lung 2. So now if this works, let's try this again here. There we go. So I've now created a new variable called age 2. And if that person is between the ages of 70 or less than 80, SQL will automatically flag it as 70. So again, if you put this into a new data frame, lung3, and you run this, you've now created that new variable, age 2, and then you can do anything that you would normally do with a previously existing variable with that new variable. So select age 2, count star from lung3, group by age 2, order by age 2, and there it is there. So again, depending on how you need to clean your data, maybe you need to do a bulk update to data that's coming in order to clean and process it more efficiently. SQL is really, really efficient at doing that. So similar to your search and replace in Excel or your mutate or transform functions within various packages in R, sqldf allows you to do this very, very quickly and very easily, and then put it into a new data frame that you can then use for reporting and analytics. Any questions or anything that I've shown up to this point?
There's a question in chat. Can
Yep.
you add age after else
Else.
to retain other existing values, please?
Yes. So what you can do is something like case when sorry, hang on just a second here. Okay, so you're going to do something like, I'm just putting this in Notepad so I can check my syntax. There we go, and paste that. So now when I run this, and then when I run my count, so I've got all the ages, except I have a gap between 70 and 80 because we've now added that as a new category. Did that answer your question, David? Yep, no problem. So yeah, so you can do that where you can have that else age end parameter, and then it'll just handle that as a whatever you have in that particular column. So again, depending on your requirements, depending on how you need to break that data down, you can do a lot of different things with it. Let me just try one other thing here. Okay. So just to highlight a couple of other things here, what we can do is something like this, and I'm just pulling this from another presentation I've done. So what I'm doing here is selecting when age is less than 50, then categorize it as under 50. When age is between 50 and 60, then put that as 50-60, so on and so forth. And these categories are going to be put into a new variable called age group. We are then going to do a count by that age group. We are going to then show a couple of different averages. And then we're going to show it where the time is not null and ph.ecog, which is just another variable, is not null. And I should actually put my backticks around that so it doesn't give me an error, and I need backticks around that. So when I run this, if everything works, yep, there it is. So now I'm looking at a different type of summary table where we've calculated age group, we've calculated patient count, average survival expired is very clearly different across the groups. Not expired is also significantly different, I would say, and the Karnofsky score is also different. So yeah, it's just another example of a query. But again, if you don't know SQL, if you're coming into this brand new novice level SQL user or even R user, and you see this as part of your documentation or as part of the code, you'll at least understand what's happening. And I find that even with ridiculously complicated SQL queries, that's usually the case. The person can at least understand, maybe not the ins and outs and the mechanics of, but at least get a general gist of the data query.
Chris, the code that you have on your screen here that
Yep,
is taking from survival, I think this would be fantastic code to maybe share in chat if folks
yep.
haven't been able to keep up, if that's possible.
I will
Um,
highlight this entire thing and I will post it in chat right now. Let me just make sure that, yeah, okay, so I am calling the library survival, install packages.
and maybe even put a library sqldf in case folks haven't been
Yeah,
following along live.
I will put that at the top because obviously that's important for that top. All right. That's it. Okay, post that in the chat. And I can post this as part of the GitHub page as well later today. Oh, apparently it's too long, so I'm gonna have to break that up into two chunks. Do. So let me do this first. And then let me see if I can slim this down a little bit. While I'm doing this, has anybody used SQL either in R or not outside of R? I should have asked that at the beginning to get a gauge on people's level of experience, but millennia, I used to proc SQL was one of the reasons why I started using SAS, and then SAS got way too expensive. So yeah, a lot of people look like they're using it. So um, thank you for coming to my talk because I was not sure the level of experience that folks would have coming into this. So I appreciate the fact that experienced users are coming and have stayed. Um, yeah, I think Milena, the last time we had a quote about SAS and not to bash SAS, but for a single year, single user license, it was $15,000 US. So I switched to R. And that's one of the reasons why I got into R was I had no other option and I had data that I need to manipulate and manage. So um, happy accident. Anything else that folks want to see or want to talk um, about SQL or just trying to find something here. Yeah, I'm just looking at other stuff that I've presented in the past, and it's all counts and averages. And what did you say? Find? Oh, so one of the things that I really like about Plotly, and again, I have never used Plotly before the working on this presentation. And the reason why I had to was because I was having problems using ggplot2 in this particular version of R and R Studio. So rather than scrambling trying to figure out what I had done wrong or where the installation problems happened. But one of the really nice things that I like, and I'm sure you can do this in ggplot2, I've never had the need to, but this interactivity. So being able to zoom in, zoom out, doing mouse overs, all of that was very, very easy to do with the Plotly syntax. Um, so it was just oh, I've got to explore that more when I have time because it definitely seems like it's easier to do those complex things further than what ggplot2 can do. So yeah. And again, not a Plotly, I'm not even a Plotly novice. I like literally just discovered this on the weekend because as I said, when I was rendering my plots in Quarto, I was getting error messages and I didn't know what the error messages meant, but they were definitely from the ggplot2 interaction. So yeah, no, and again, feel free to email me, Sandra, if you find anything that's useful or any good resources on Plotly, because I've never used it, but I know it's very, very common and very popular. So again, it goes back to you use the tools that you know and you use what you're comfortable with. And um, yeah, I'm just looking at my notes here from other presentations and I'm not finding anything other than what I've already shown, just using different data sets. So if you do have any questions, I mean, please do feel free to raise your hand, post them in chat. We got about another hour left, so I don't want to waste your time by just showing you the same things over and over again, but I want to make sure that you have time to ask. And oh, good question, David.
Can you
So
do me a favor, Chris?
yeah,
Since we're going to record this, do you mind just reading the question?
yes,
Uh,
of course. So David is asking, when joining, do you need to have the source table in the same working path? Again, to be perfectly frank, I don't know because I've never had to do it at that level. I've always just imported the data as a data frame into my R environment. Typically, the data frames and the data sets that I'm using are quote unquote small in that they fit on and they run perfectly fine on my local laptop. I do have a couple of instances where I've needed to move my data to my server to run it on my server environment. But the joining is always been, once you're pulling that into the R environment, I've never had any problems referring to tables across or within that same environment, if that makes sense. Can SQL, yes, actually, that's a good, hang on just a second here. So the question was, can sqldf allow for subqueries? And yes, they can. They're just a little different from what you might have experienced using others, where there are some limitations based on the SQLite engine that it relies on. Um, you could use subqueries to filter, for example, aggregate or manipulate data. So if I'm using actually, hang on a second here. Uh, du- 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 du. Sorry, I'm just trying to find some notes that I have. There we go. Okay, so here is an example of a subquery where I'm using the lung data again. I'm selecting age group. I'm doing my counts and averages, but then within the subquery, I'm aggregating and doing that uh, combination. So when I run this, oh, again, I forgot the backticks. Sorry about that, folks. Hang on just a quick sec here. PHCOG. And these backticks are not normally found in other SQL environments. So if you're running this query in SQL Server or in a MariaDB backend database or MySQL or Postgres or whatever, these backticks are going to give you error messages. This is one of those remnants from R or artifacts from R that does need to be taken into account. There we go. So now when I run this query with this nested subquery, this is the result that I'm getting. So again, you can do, I would say probably 80 to 85% of what you could normally do in a SQL Server environment. There are some things that you need to take into consideration, like backticking, variable names that have periods or special characters or spaces is another one. So again, if you're comfortable using it, use it, and it allows you to do a lot more, at least in my experience. Yeah, of course. And I will post this in the chat too, David, just for folks that want to have a copy of this example of a subquery.
this isn't a question as much as it is, I guess, an exhortation, which is for those of you who may have never used SQL or infrequently used SQL and you really love dplyr, I love dplyr as well, and I use it a lot. But SQL is a really great tool to add to your toolkit, especially if you need to talk to people outside of the R sort of world. If you need to talk to data engineers, if you need to talk to people who work in Snowflake or BigQuery, or who work in Epic, who work in Chronicles, who work in Cerner, who work in your big data backend, because SQL is as close as we come to a universal language when it comes to data. And while Chris pointed out, there's a couple of small things that might throw an error from SQL dialect to SQL dialect. Those differences are quite small. So if you are able to form a query using SQL in R that works for you, that query will make sense for people outside of your practice area in a way that dplyr code will not. So it's just a really good tool to add to your toolkit. If it feels like a stretch, I just really want to exhort you to give it a try.
Yep. Yep. So I just found my ridiculously stupid, complicated example of a query. SQL is yes, it actually stands for SQL for data frames. So yes, to your the guest's question is SQL is only for our data frames, right? Yes, it is only for our data frames, and the DF is actually stands for data frame. Um, so what
That
I've got, sorry.
Oh, I was just going to say, however, there are ways to use there's other libraries in which you can use to use SQL, for example, with BigQuery. And there's other ways to use SQL. So sqldf is for data frames. But if you use SQL in other ways, there's other libraries as well.
Yeah, and that's where I am self-taught in everything that I know about R. So when I started learning and I heard terms like tibbles and matrices and vectors, I went, huh? And then I heard data frame and I'm like, what? And then it's like, oh, it's just an Excel spreadsheet, but in R. Oh, okay, I know what to do with that. And then that's where I discovered things like the tidyverse and got more and more into the tidyverse philosophy. And so, yes, sqldf is specifically for data frames, but again, as I mentioned at the beginning of my presentation, there's a whole ton of other packages that allow you to do stuff using SQL. I've just never had the need to do that. Um, so this is an example. This is my ridiculously complex, you know, example of a SQL query. So when I run this, I hope it runs. It's been a while since I've run this query. Did that run? Rank Kanofsky? Yes, it did. Huh. So one of the nice things about this query is it really, and I'll put this in the chat as well in a second, you can do things like row number over partition by case. So you can rank particular scenarios and particular categories based on criteria. So if you want first, second, third, fourth, you can do that by using this kind of a syntax. This is also showing a couple of different subqueries that are being used. So you're taking your big data set, you're filtering it, you're manipulating it, you're rerunning the query, you're doing other things with that. I'm calculating a couple of different percentages and that sort of thing. Offsetting is where you can have offset your limits by, you know what, I can't, hang on a second here. Going back to my notes here for a quick second because it's been a while since I've looked at them and I can't remember what offset does. Oh, right, of course. This is why I take detailed notes. It skips the first row. So it'll show you and this is something where you've run multiple queries, you've done your due diligence and data exploration, you've started to build that story where, okay, you only want to see specific criteria or specific things. Offset allows you to do that and just sort of drop your data returned by X number of rows. So this is where you can get into, again, as Joy was mentioning, like you can get really, really cool stuff, but it's all very complicated. But yet, if somebody read this for the first time, they might not know the details. They might not, be able to see where the errors are. They would be able to see what this is doing and what this is pulling. So I'll put this in the chat as well. Ridiculously complex. And of course, this one is again over the chat limit. So let me try this. And again, this is where formatting aesthetics versus saving space becomes a big deal, because I am just going to remove any extraneous lines. And hopefully I can get this down to a limit that I can post back in chat. Does anybody else have any other questions or want to see anything again? Or, yeah, I mean, this is your time, so please feel free to.
I'll read
Oh,
a question from chat. I am
yeah.
definitely an infrequent SQL user, especially with R. You mentioned that one strong point for SQL is its ability to do joins. Do you find joins in SQL to be easier than in R?
Most emphatically, yes. um, because I have never found a way that I can easily remember to do left joins, right joins, not that you can do right joins, but left joins and that sort of thing in base R or in a package within R. Again, I've got 25 years of experience using SQL. I've got probably 10 using R. Again, never been trained on either one, but I go to what I know. So in my mind, seeing two tables, knowing that I have to do a left join is a lot easier for me to think through than trying to figure out that same syntax using a package. Um, so yes, definitely think it's an easier thing to do in SQL. But again, like I said there to somebody else the other day, I always love to be proven wrong. So if you have a way to do joins that's a lot simpler, I would love to see it, because I'm always willing to learn new things. And I'm just trying to clean up this complex code here so I can paste this in the chat. So just give me a quick sec here. Ba, ba, ba. To that point, has anybody found an easier or alternative way of doing joins between multiple tables?
Well, dplyr now does support left join and inner join, so it has more of a SQL join sort of structure. I think a lot of us learned to use merge when we first started with R,
Hmm,
which sort of defaults to an inner join. And if you use merge, you have to be a little bit more verbose, right? If you want to do a left.
right.
But I think dplyr is a little bit more supportive of SQL type joins now um, than it was when it was first launched. If I
Hmm.
if I if I'm if I don't miss my guess.
Milena, I do like your comment that SQL seems to be the best error-proof approach. I fully agree, you know. Um, and again, I'm biased. I appreciate the fact that I'm biased, but I have never found anything that is close to what it can do. David says, I agree, SQL joins are useful and very flexible. Yeah, and um, I'm recently, I've recently had to start dealing with a very complex database where there's fact tables and dim tables and everything else, and being able to not have to worry about thinking how I do that join. I just do the join because I know that in the fact table, there's patient ID, and that's going to be in the dim table, and that dim table connects to another dim table, and so on. It just allows me to be that much more efficient and spend my time going through errors and data quality stuff rather than trying to figure out how I do X, Y, and Z. And then part two. There you go. Okay, so I had to split that ridiculously complicated query into two parts, but it is now in the chat as part one and part two. So, and for those of you that are interested, I'm giving a talk at 4:30 this afternoon on validating packages in R for regulatory compliance. I don't talk about sqldf, but it does go into how you need to make sure that your R packages are compliant using test that, and I go through an example using the assert that package. So again, if you're using SQL for a clinical trial and you need to have that proof of documentation and proof of validation, in my mind, giving this type of a query to an auditor is a lot easier for them to read and understand than some sort of complex mutate X, Y, and Z sort of R syntax. So, and again, I don't know, I've never had to provide that level of detail to an auditor, so I don't know what they would look for or what they would need to have. But in my mind, the easier the document is to read, the easier it's going to be to have that conversation with them. Any other questions, comments, thoughts? With FDA, our audits always follow queries with row counts. Yeah, yep, that's a good point, David. That's again going back to um, one of the points that I try and make in the talk that I'm giving this afternoon is if you've got transparency, if you've got the trail, then you should be fine. But having that level of detail is really, really important.
Well, if there's no additional questions, what do you think, Chris? Shall we give folks a little bit of extra
All right.
time back?
I am more than happy to give folks time back. It's one of those things where in my mind when I was doing the run throughs and everything, I'm like, whoa, man, I'm going to be right on time. This is perfect. And then it's live and it's like, oh, okay. So, yeah, I appreciate everybody's patience going through this. And as I said, feel free to email me if you have any questions, if you want to have a further conversation about sqldf or whatever. Um, I'm the RedCap admin at my institution as well, so always talking RedCap and R is always something that I love. So yeah, feel free to reach out if you have any other follow-ups. And I will get the GitHub cleaned up by end of day tomorrow if everything goes according to plan.
Well, we're really grateful for all the information that you shared with us. We know how tricky it is to do live coding, and so we appreciate the vulnerability that you shared, and working together to solve problems. I think that's how we learn together. And so I think that is some of the most important and intuitive learning that we can do as an R community together is coding together live and figuring out how to solve problems and what to do when you get an error message and how to solve those problems and realize let's put in backticks and figure out what to do when something doesn't respond the way we thought it would. So we really appreciate all the syntax, learning how SQL joins work, learning a little bit about the history of SQL and how important it is in sort of the history of relational databases, how fundamental it is in so many of our systems and how it really underlies a lot of the institutions where we work. So
Yeah.
thank you, Chris. I can really tell the care that you put into this workshop. So again, thank you so much. We really look forward to your is it 4:30 presentation this afternoon?
Yeah, it's at
So
4:30 this off. So um
excellent.
yeah, looking
All
forward to it.
right. Thank you so much.
Thank you all.
And everyone, have a great rest of your afternoon. Please take a look at the rest of track A and track B. Feel free to jump into chat on the main R Medicine portal. Let us know what you're thinking. Let us know what you enjoyed and what you're looking forward to. And we will see you in the upcoming talks. Thanks so
Bye
much,
for now, everybody.
everybody. Bye now.